Hello, good afternoon, everyone. I welcome you all to the International Symposium on Revolutionizing Medical Imaging with Computer Vision and Artificial Intelligence, organized by Amity Institute of Biotechnology, Amity University, Uttar Pradesh, in association with Indiana University, Purdue University, Indianapolis, IUPUI, USA. Artificial intelligence is the game changer of the era. Almost all disciplines of science and technology is now dependent on decoding the unpredictable by the diverse possibilities offered by the AI. And what better could it be to revolutionize medical imaging, as it would be a boon for the healthcare sector? On this auspicious note, let us begin with the Saraswati Vandana. That was really divine. I would now like to invite Professor Dr. Seema Bhatnagar, Assistant Director, Coordinator, International Initiatives, Amity Institute of Biotechnology, to please deliver the welcome address. May you please, ma'am?
Thank you, Devlina. Dear esteemed dignitaries, speakers, faculty members, students, and my dear friends. It is with great pleasure and honor that I welcome you all to the symposia, Revolutionizing Medical Imaging with Computer Vision and Artificial Intelligence. Today, we gather here to explore the exciting intersection of cutting-edge technology and healthcare innovation. This symposium promises to be a thought-provoking and enlightening journey into the world where artificial intelligence and computer vision converge with the field of medical imaging. Throughout the next 3 days, we will have the privilege of hearing from world-renowned experts, researchers, and practitioners who are at the forefront of this revolution. They will share their insights, experiences, and discoveries, shedding light on the incredible potential of AI and computer vision in the realm of medical imaging. From exploring the nuances of image analysis and interpretation to unraveling the complexities of deep learning algorithms, we are poised to gain a deeper understanding of the profound impact of these technologies and that they are having on healthcare. As we delve into the symposia's sessions and workshops and discussions, I encourage students to actively engage and collaborate. I hope this symposia is not just an event, it is also a platform for fostering meaningful connections, sharing knowledge, and sparking new ideas. The challenges we face at the intersection of AI, computer vision, and medical imaging require interdisciplinary collaboration and a collective effort to drive progress. I take this opportunity to express my gratitude to Honorable Founder President Sir, Chancellor Sir, Vice Chancellor Ma'am, and officiating head AIB for their support and blessings. I also would like to extend my heartfelt gratitude to all the organizing committee members, sponsors, and partners who have worked tirelessly to bring the symposia to fruition. In conclusion, I am excited about the possibilities that lie ahead during these enlightening days. May the symposia serve as a catalyst for inspiration, discovery, and collaboration as we explore the limitless potential of AI and computer vision in shaping the future for medical imaging. Thank you for being part of this incredible journey, and I wish you a very productive and enriching symposia. Thank you very much. Over to you.
Thank you very much, ma'am. Thank you for the very warm welcome. I would now request Professor Dr. Pooja Vijay Raghavan, ma'am, officiating head, Amity Institute of Biotechnology, to add some of the vital remarks on this occasion. May you please do the honors, ma'am. Thank you.
Am I audible? Am I audible? Okay, thank you. Good afternoon, everybody. It is my utmost pleasure to share my thoughts today on this very, very important and need of the hour symposium on revolutionizing medical imaging with computer-aided vision and AI. At the outset, I would like to congratulate the team that worked tirelessly for the symposium, Professor Dr. Seema Bhatnagar, Dr. Kamal Rawal, Dr. Priyanka Narad, and their very, very able team of faculty members and students. This remarkable convergence of medical imaging, computer vision, and artificial intelligence has given birth to a new era in medicine, where diagnostic accuracy, patient care, and treatment outcomes are being transformed in ways that we could hardly have imagined a few years ago. Medical imaging, powered by AI-driven computer vision, enables faster and more precise diagnosis by swiftly analyzing vast amount of medical data, such as X-ray, MRI, and CT scans. Dr. Kamal Rawal is also working on these technologies. This conference, where around 100 students and faculty members are taking part, they will get an opportunity to grasp these cutting-edge techniques and position themselves at the forefront of this transformative wave, gaining a competitive edge in their future careers. As AI and medical imaging technologies have become increasingly integrated, the employability of individuals who are well-versed in these areas will soar, and they'll become essential assets in hospitals, research institutions, and healthcare companies. And by giving these opportunities to students of Amity University and other universities, we are giving an opportunity to the students to explore this facet of healthcare. By embracing these skills, students are not only ensuring their own professional success, but are also contributing to the healthcare revolution that promises better patient outcomes and improved quality of life for countless individuals. We are very, very thankful and elated that Indiana University, Purdue University, Indianapolis is associated with Amity University in organizing this very important symposium. We thank Dr. Sarat Janga and his team for this association, and we hope that this is just a start to a wonderful and highly lucrative future. This will be a great platform for discussing and deliberating future endeavors in this area, and we are very sure that very soon we will be able to witness extremely tangible outcomes. With these words, I once again congratulate the organizing team, Dr. Seema Bhatnagar and her team, for this wonderful conference. And I'm very sure that everybody who's associated with this symposium, students, faculty members from Amity and from universities outside Amity would highly benefit from the symposium and would learn something which would add value to their curriculum and for their employability. Thank you so much for giving this opportunity. All the best. Hello.
Yes.
Thank you.
Thank you very much, ma'am. I would now request Dr. Priyanka Narad to take us through the vital or the key points of the conference and what are the benefits and the key advantages that the students or the collaboration team are going to benefit from this. May you please, ma'am?
Hello, everyone. I hope I'm audible. So, a very warm welcome to everybody who has joined us for this symposium. As this symposium is based on the theme around medical imaging, which is an emerging area in the field of artificial intelligence and computer vision. So, as already stated, this symposium has been organized in collaboration with Indiana University, Purdue University, Indianapolis, IUPUI, USA. So, the symposium is through 4 days. Day 1 is today, where we start with 2 keynote address, and these will be delivered by Dr. Jayadeva and Dr. Sarat Janga. This will be followed by tomorrow, which will have a lecture and followed by a hands-on session by Dr. Vanathi Sundaresan from IISc Bangalore. This will be followed by a lecture again, which will be by Dr. Animesh Acharji, who is a Deputy Program Director at the University of Birmingham, UK. And lastly, evening sessions will be from Dr. Sarat Janga, IUPUI, and followed by the hands-on session. So this is what we are having on day 2, that is tomorrow. The session starts at 12 p.m. and it will go on till 7:30 p.m. for the IST timing, and since IUPUI it is morning there, so we will continue till 7:30 p.m. in the evening. On day 3, we start at 1:30 p.m. by Dr. Rintu Kutum, who is a assistant professor and faculty fellow at the University Trivedi School of Biosciences, Ashoka University. He will also take you through an hands-on session where you will be doing some hands-on on the medical imaging. This is followed by an industry lecture by Mr. Ravi Kumar Kushwaha, who is working as an AI research scientist at Cure AI, which is one of the leading organizations who work on the medical imaging data. Then in the evening, again, we'll be having speakers from IUPUI, where they will be taking you through some lectures on the advancements in the field of medical imaging. There are 3 lectures lined up by different professors from IUPUI in the evening, and this session will also end at 7:30 p.m. in the evening. And day 4, we will be having session which will be starting at 10 a.m. by Dr. Kamal Rawal, who is the center head at AIB, who's heading the Center for Computational Biology and Bioinformatics. He will also be taking a hands-on session on the same, and this will be followed by oral presentations by our students who have submitted their abstract. And then in the afternoon, we will be having a valedictory session where we'll be having chief guests from various organizations such as ICMR, a medical doctor who will be sharing his insights, and a panel discussion into how AI is changing the landscape of medical imaging, its benefits, limitations, and ethical and legal considerations, which are also one of the important segments in the days to come, because ethical guidelines is something which is very, very important when we implement anything using AI. So this is what we have lined up for all the participants. All the participants are requested to join the sessions regularly. There will be a quiz at the end of each day. So each day after the last session, there will be a link of quiz which you will have to attempt. This is not going to be a very difficult kind of a quiz. It just relates to your presence, and it helps us identify what better we can do in the next symposiums to come. So this is what we are hoping to gain. And please participate with your full enthusiasm, and you can ask questions to the speakers, and also in hands-on sessions. You are most welcome. I'll be sharing some instructions for the hands-on session. One such instruction I've already shared in the group that is with the participants, that please download some softwares for Dr. Janga's session tomorrow, which is a prerequisite for doing the hands-on session with Dr. Janga. For Dr. Rintu, we have everybody, I'm sure everybody here is familiar with Google Colab. So you please log in and access your Google Colab there, so that you are able to work through the basic experiments that are being conducted by Dr. Rintu Kutu. So these are the two requirements that have been shared by the speakers, and we look forward to having a great symposium ahead. So please be attentive and make the most out of it. So I thank everybody for joining in, and we'll soon be joined by our first keynote speaker. So as soon as we have you, we are going to start with our first keynote lecture.
We are glad to invite Professor Jayadeva, GSV Chair, Professor and Head Department of Electrical Engineering, IIT Delhi, to deliver a keynote address on the title AI/ML Challenges for Medical Diagnosis. Professor Jayadeva jointly formulated an algorithm to detect rare clusters that recently appeared in a Nature Communications paper on finding rare cells in large-scale RNA data. He pioneered the twin SVM that has nearly 1,600 Google citations and is the subject of multiple review papers. The twin SVM is not sensitive to class size imbalance and is widely used for medical data sets. He showed how to use bounds on the VC dimension to learn sparse models. The minimum complexity machine yields models with accuracies comparable to the SVMs, but whose sizes are 3x to 10x smaller. He was amongst the first to design and realize an SVM-based AD converter in 2006. The design demonstrated a new approach to self-calibrating designs. He originated the EigenAnt, the first ant colony optimization ACO algorithm with stability and convergence proofs. His group's EigenAnt-based router is possibly the first ACO in VLSI. This work was presented as an invited keynote at the IEEE SSCI Singapore 2013 and featured in the HT Mint. He was amongst the first to solve combinatorial optimization problems using PLL arrays. He has co-authored books on numerical optimization with applications and twin support vector machines, model extensions, and applications. He is a fellow of the INAE and the IETE. May I now invite Professor Jayadeva to deliver his keynote speech. May you please, sir?
Yeah, is it okay now? I don't know why it got muted.
Yes, sir, we are able to hear you now. Thank you.
Thanks. And you're seeing my slides, right?
Yes, we are. Thank you.
Okay, so thanks. So thanks, Dr. Bhatnagar, for inviting me to the symposium. So I will just give you an idea of some of the work that we are involved in. All of this, as you can imagine, is collaborative work because it involves people from the clinical as well as biomedical domains, and of course, our work primarily in the AI and machine learning area. So let me give you some examples of what's going on. So this is a device that was invented at IIT Delhi by Professor Ravi Krishnan Elangovan at the Department of Biochemical Engineering and Biotechnology. It's called CTB, and the idea is, can we automate the diagnosis of TB, which is widely prevalent and it's actually a serious problem. So right now, the methods for doing that are slower and more cumbersome. And the idea is, can be automated by using essentially some kind of a microscopic technique along with AI and machine learning. So I'll come to that if there is time. The more important kind of application is something like this. So this is called CTB. This is the device. So cervical cancer is one of the, is a very common cancer with high incidence in India and fairly high mortality rate. It's fourth common among women in the world, and in India it's a third common among women. So what you have is if you take a sample, which is using what's called a pap smear, what you get is you can get cells which look, of course, this is normal, And then there's an intermediate or a low grade kind of squamous, stage, which is called LSIL. And this progressively moves to HSIL and eventually, what you call as cancer, or what you term as cancer. And you can see the density of nuclei, is much higher in the last stage. It's increasing gradually, and is one of the features that can be used to detect the presence of cancer. So what we wanted to do was, of course, we want to automate this entire process. And in order to do that, let's of course go to a bit why it is so important, what's currently done, and so on and so forth. So I'm not going to, of course, read out from the slide. I'll let you kind of look at the slide. And thanks to Professor Elangovan for helping me with the slide. Well, it's his slide essentially. And what we are trying to do is using this device called an otoscope, which will come on the next slide. So what do you do in a PAP test? You take a sample, then there's a smear preparation, then there is staining, and then of course the pathologist looks at it under the microscope to determine what's the grade of the cell. Is it LSIL, HSIL, or cancer, or something else? And in order to complete the staining process, of course, we need multiple kinds of stains. And you can see at least, we have eosin and one more hematoxylin. Now, the difficulty is that this process is cumbersome. It's time consuming. What you would want to have is something that's automated and fairly rapid. And this is the device that we have. Essentially, it's an automated microscope. So what it really does is it takes an image of the complete slide, and that image is then automatically processed. But it also, the latest generation of this device does all the staining in an automated fashion. So that allows also uniformity in the data generation process. So many of these problems actually will, when you look at them firsthand, you'll realize that the data generation is as critical or as important as the data analysis. It's not just about taking the data in a file and analyzing it. Very often the noise or the confusing inputs in the image are coming because the data preparation or the preparation process itself is not perfected or automated. For example, if the staining is done manually, you'll have variability depending on who does that, what kind of materials were used, and so on and so forth. So the idea is that within 10 minutes, you want to have a complete output from this device, including the AI machine learning part, and then you want to generate some kind of a diagnostic report. And the idea is eventually even the report would be an automated document. Okay, so here is something that you can look at. What you see on the left are essentially these are normal cells detected correctly. It's an auto stained slide. That means the staining was done automatically and captured using this otoscope. And on the right side, there are correct, there's a correct identification of HSIL or LSIL kind of cells. So what you can see here is there's a lot of variability in the data itself. One, of course, LSIL and HSIL are categories, but within each category, you will see a large amount of variation. Second, you see many categories. It's not just that you would have LSIL, HSIL, and normal. You also see other, let's say, confabulating or factors that will create confusion. When you have many categories to put the data in, we will see that machine learning also gets confounded by having to determine one of many classes. So what I'll try to do during this talk is try and connect some of the challenges from the machine learning side and tell you with, for instance, the real problem at hand, what is the difficulty on the AI or machine learning side, and some of the techniques that we have developed to take care of that. Okay, so just to acknowledge all the people involved in this, it's a fairly large set of researchers involved in this. This funding is from multiple agencies, and of course, there are also clinicians involved in that, from ICMR and Safdarjung Hospital and so on and so forth. So multiple departments. Also, there's a whole team at this startup that is there, which was incubated at IIT Delhi. Okay. So the other problem I'll come to a little bit later is an interesting problem, and this is a collaboration that we are doing with Dr. Vineet Bhatta in the United Kingdom. And this is something like, you want to identify the implant. So, when people, at least, many elderly people undergo or have a hip fracture, very often you need to replace this entire joint, and this is an artificial implant. So here is actually the implant, which is looking bright white, and it's embedded in the bone. So really, you have to drill through this bone, create a an opening for it, and eventually it's cemented. So it's actually bound with some kind of cement into the bone. Eventually, it becomes kind of, the body accepts it as part of it, and there is also bone that grows around it, so calcium deposits around it. So eventually it becomes like a part of the femur itself. Now, many years after such a surgery is done, it's called an arthroscopy. Many years after this, what happens is that sometimes there are problems with this implant. The problems could occur, for example, in this cup. They could occur here. There are many parts of this, and unless I show you a very detailed or go through a very detailed discussion, all these parts won't be clear. But the idea is, when such a problem occurs because of an implant that has been there for 10 or 15 years, the surgeon has to do something called a revision arthroplasty. He has to go back and do something to fix the problem. So sometimes this cup has worn out and is creating an issue. And when you do that, you don't really want to go back and say, let's put in a new implant altogether, because that's a difficult surgery. It's also fraught with many more risks to the patient. Instead of that, can we just replace the part that's involved? Right. So that's that should be simple enough. But the challenge is that the implant itself isn't made by just one manufacturer. There are a large number of manufacturers who make implants. All of them differ from each other, in small ways or sometimes in major ways. So these parts are all different. And at the same time, each manufacturer might have multiple variations or versions of the implant. So the problem is that when the surgeon has to look at this and decide what to do, very often the patient is in the hospital because they have had, or they are with a problem, and now you have to decide to operate within a day or two. And if you want to do that, you want to know what was the implant that was put there. So you can go to the manufacturer and say, I want this part, I just want to replace that, and get this done with quickly. And here is the problem. The problem is, from this image, I don't know what implant was actually put there in originally. And in most cases, hospital records don't mention in detail the manufacturer, the part, and so on. So what you would like to do is, really, if I give you this image, can I use machine learning to identify which was the implant, what was the brand, what was the make, what was the version number, and so on and so forth, and quickly tell the surgeon this is what is needed, so that the hospital can get that part and go ahead with relieving the patient of whatever difficulty they are in. Okay, what makes these tasks difficult? So I'll come to at least one more later on, and the problems are several. One, there's a very small number of labeled samples. For example, let's take, for instance, the case of cervical cancer. We can have a large number of slides, but the number of automated, slides with uniformity in the staining and all is small. And most of this labeling is done manually. So you could imagine I could manage a few hundred, with a lot of effort, you could do a few thousand. But if you're looking at big data, we are talking about millions. That's not going to happen. Also, certain kinds of samples which are rare are difficult to find. So if you want more categories and you want to look at them all with equal accuracy or uh, adequate accuracy, you may not get samples for all classes. For example, in the case of the hip implant that I showed you, for some of the implants, there are very few patients who got them. So the number of images is very small. So we may not be able to get them very easily. We may have 1,000 or 10,000 images, but we only have 5 or 10 of a certain kind. Then there's imbalance in the size of classes. So if we look at the staining that I showed you for the cells, in cervical cancer, you have normal, HSIL, LSIL, and cancerous. At least these 4. Well, there's a 5th one, but you would imagine that normal would be much larger than the others, because in the case, the cancerous ones are usually at an extreme stage of the, let's say, the disease. So in early stages, most of the people would not, and if most of them are coming in for screening, then most would be in normal. So the size of the classes, the number of samples in these classes is very different. Normal is very large, others are much smaller. Third is the dimension of the data. If you're looking at images, the number of pixels is large, maybe, ranging from a few or several thousand to a few million. Then, of course, there's another problem. The data is not normalized. So let me go back to that X-ray image and tell you, very often this X-ray is not going to be very aligned. So the implant will appear at a slight angle. It will be slightly tilted. The patient is not able to lie normally. So, the X-ray has not been taken in the same way as others. So there's a lot of variability, because of which recognition is impacted. And finally, some categories are really rare. And this will come to towards the end of the talk. Right. So let me, start with an anecdotal slide. And, you look at this slide and, the question is, well, what's really, a problem with this image that you see? Is there something wrong here? Or is there something that is not okay? And you would think, well, this is, this might be commonplace, in certain regions and not so common elsewhere. But the simplest answer to this is, well, maybe there is no problem, but there is a good chance, or there's a probability that someone, will land up with a difficult situation, right? Or there may be somebody might get injured at the end of it. So the question is, what is the chance? So this is more of a question on probability. And if you want to answer it, what's the chance that a trip on this bus will not end in failure? And by failure, we mean that, or success, we mean you get off at your destination without any incident. And if there was some incident with any of the passengers on this bus, then we'll call it failure. So what's the probability that a trip on this bus will not end in failure? And you could answer it by looking at the following. One, you could say, how often has this bus made a trip without any issues? So if it made 1,000 trips and it did not have any issue with 900 of them, you might say, the chance that problem occurs is like 10% or less. So how much of data do we have on how often this happened, or how many trips were made, and how frequently did an issue arise? So this is the first part, and it's more about, it's really, what is the empirical measure of success or failure? And this is really empirical risk. It's like saying empirically, what's the risk, or what's the chance that failure happened? The other part is how crowded the bus is, right? How many degrees of freedom are left? And this is really saying that if you have many people on this bus, so if all seats are taken and it's overcrowded, the people on the top and at the back and so on, clearly speaking, the probability of some kind of failure is high. And in machine learning, we can associate, this anecdotal kind of connection with two kinds of risk measures. The first part, how many trips were successful out of say 1,000? Well, that's the empirical risk. And the second part is really how many degrees of freedom are left is really what we call a structural risk. And this is really the part that has become interesting in more recent years. So the overall risk of failure depends on both of these, right? And the first part you can imagine also depends, for instance, on the condition of the road, on the condition of the bus, and so on and so forth. And this first part gives you a measure how likely you are to have a problem. And the second part really is telling you that, uh, this is something that has really no direct connection with the empirical risk part. And finally, of course, despite having both these measures, you could still have a problem. And that's really saying, where are you most likely to encounter failure? So if you had a machine learning model that is trying to predict, the first part is over all the samples that you gave for training, how many times did you classify training samples correctly? And that's your empirical error. The second part is the structural risk, right? How complex is the model? How many degrees of freedom really are left in that model? And finally, despite having, let's say, a good success rate on training samples, and even if you have a very small model, which means the structural risk is small, you could still have somebody who falls off by accident. So the rare chance that something goes wrong still can happen. And for instance, it can happen in real cases with outlier samples in the test data set. Okay. So just to summarize that, and my work in machine learning is really connected with trying to minimize the total risk. And more often recently, we are looking at ways of minimizing the structural risk. How do you learn simple models that, that can give you good empirical, accuracies, but on the training data, but also small models. And this allows us to have greater, let's say, control on how good the model will generalize. Right. Okay, so I'm not going to show you too many, say, equations in this entire presentation. The idea is to keep it simple, but if there are questions, one can look at that. And this is a risk formula that Vapnik gave, many years ago, decades ago. And what this says is that the probability of making an error on overall the distribution, which means on the test data that comes after you have finished training the model, is bounded by the error on the training data and this other term. So if you look at this other term, you will see that you can roughly ignore the 1 plus, you can ignore this as well. And so if you just multiply the b epsilon with the square root here, you can see that's roughly proportional to b under root of square root of epsilon. So what is this epsilon here? This epsilon is essentially this complicated expression. Just ignore the last part, the delta, we can look at it subsequently. M is the number of samples. So the more training data you have, the smaller or less significant the second term is going to be. And even though you have M here, it's a log M here, and M grows much faster than log N. So eventually with large enough data sets, the second term really becomes insignificant. And that's why big data is useful, because it doesn't matter what you do or what kind of model you learn, you're likely to do reasonably well or equally well really with almost any method if you have enough samples, which means if M is large. If M is small, then you have a problem, because then this term becomes important. And then we have to worry about what's called the VC dimension. The VC dimension, we won't get into it, but it's a measure of how complex the model is, how difficult, how complicated the model is, right? And that is something that is going to become very important if you have a small number of labeled samples. So the idea is when you have a small number of samples, keep the VC dimension small. Right? And how do you do that? Well, that's actually one of the interesting challenges in machine learning. And like I said, there is an uncertainty despite all this, and that's this delta. What it says is that, you know, this is true, but with some confidence. It's like saying if delta is 0.2, I'm saying with 80% confidence, I'm saying that this bound holds. So you're saying something like with 80% probability, I'll get a good, classifier. Right? Now, we'll come back to the slide, but let's see what all you should do in order to keep this overall, the right-hand side small. One, of course, do well on training data. Second, keep the second term small. How do you do that? Have many samples or keep VC dimension small. Okay. In neural networks, the VC dimension, it just went back. So in neural networks, the VC dimension is related to how many weights you have in the neural network, how many connections and how many neurons and so on. So methods like dropout or drop connect, which reduce the number of weights in the neural network, reduce the VC dimension. If you're familiar with support vector machines, then the number of support vectors is connected with the VC dimension for methods like kernel support vector machines. So in both cases, some form of methods of pruning, reducing the number of support vectors, reducing the number of weights in a neural network are useful in keeping the second term small. Okay. So I just simplified it. This roughly saying this is under root this epsilon and so on. So, you know, it's just a summary of what I just, told you orally, right? So in the context of machine complexity, the moral is use the simplest solution for a given task. That means keep the complexity small. Use the one that will be least likely to fail on a given task. And, you know, machines that are less likely to fail in a prediction task will generalize better. So that means a simpler model tends to work better. And of course, you know, the exactly like I showed you in the figure, when all of your degrees of freedom are getting used up, you will actually overfit. Okay. And so that's exactly what happens, even otherwise, but also in the case of learning machines. Okay, so here is just a sketch of what a neural network looks like. So I'm sorry if I don't know how the colors appear on your screen there, but maybe it's not the best choice of color. But all of you know what a neural network is. It's a set of layers, and there are some neurons in each layer. There are input weights to each of these neurons. The output of one layer goes to the next layer. So it's a feed-forward neural network. And normally you have connections from one layer to the next layer. These are connections from layer 1 to layer 2. Sometimes you can have leapfrog connections, which means connections that cross layers and connect to a neuron in some later layer. Right? These days, of course, for image analysis, we tend to use convolutional neural networks. And the main reason is when you have very large number of neurons in the input layer, when you have very high dimension, instead of wanting to use many different weights, the idea is, can I use a smaller set of weights and repeat them across all the connections that are there. So that's what convolutional networks do. They do weight sharing, local connectivity, and they also bring in translational invariance, which means it doesn't matter where the shape C is, could be anywhere, but will give you the same kind of, result. So I'm going to skip this. It's a CNN architecture, but okay. So let's look at, some more interesting things. Where does the confusion come in from? So what is this sketch? This is a sketch, or it's a plot of the data in a binary classification problem. So the red is one class, the blue is another class. And you can think of that the plot that you're seeing here, although the input is not two-dimensional, it's a kind of projection onto the two principal components of the input dimension. That means the two most important, let's say, directions where the information lies in the input dimension. Clearly, in the input space, the blue and red have a lot of mixing. In other words, there's a lot of confusion between the blue and the red. What the neural network is able to achieve, it's able to separate. So this is at the output layer, and you can, or really a layer before the output layer. You're now seeing that the blue and red have some separation between them, and this is reducing the confusion between the blue and the red. There is another thing that you should notice. You also notice that if you look at the vertical axis here, this is going from minus 0.6 to 0.6, and this is from minus 0.1 to around roughly plus 0.1. So this is actually on the original scale, this will look more like a dot. So what we've really done is we've taken these two distributions and we have mapped them to a space where the blue is now really like a dot. It's just minus 0.1 to 0.1. So that's somewhere like, you know, a dot about this size. Slightly bigger than this blue dot you see here, but a very small dot over here. That's the size really of this entire blue distribution. And similarly for the red. And between the blue and the red, now there's a fair gap. See the scale on the x-axis, it's between minus 7.5 to plus 10. So actually there's a fair bit of separation between most of the blue and most of the red. So what the neural network has done is reduced the the variability within the blue. So it's shrunk the blue to a dot, shrunk the red to a dot, and then it's moved these two away from each other, right? If you look at multi-class, this is a problem with digit recognition, you know, a database called MNIST. So those of you who know, MNIST has 10 classes, all digits from 0 to 9, handwritten digits. And here there's a lot of confusion. And you can see finally in the output layer, all these categories have got separated very neatly. They are well separated. And, you know, obviously we expect that if you had tried to predict whether an input is, you know, digit 0 or 1 or 2 or whatever, you would do very poorly in the input space, but you obviously are going to do quite well here. In order to do this, you want good separation between all these centers. And that's really what we refer to as the margin between classes. Here as well, if you look at the classification of cancer cells, we have multiple issues here. So we have multiple categories. So just like in the previous slide, I want the normal HSIL, LSIL, and others to be well separated from each other. I want them to not have too much of variation, because then I might make a mistake between the closest group here and one of them here. And additionally, I have other difficulties, which is, as I mentioned earlier, the number of samples in HSIL, LSIL, or these different categories, they're not equally populated. Some are more common than others. Okay, so we'll come back to that question which I asked, you know, what are the difficulties that we face, and some of the ways we are trying to solve that, right? This is, of course, the orthopedic implant one. And remember, what do you do about small number of labeled samples and data not normalized? So if you remember in the implant, I said X-rays are often taken without really any alignment. You know, they could be taken at different angles. And this variation actually causes us to confuse one implant with another when we try an automated pipeline, right? So here is roughly, you know, the sequence of steps which we use to go through all this, right? What we've done here, and, you know, this is a question that you might want to take a guess at. So what we've done here is we have added new samples or additional samples of implants, additional implant images into the data set. And some of these are from the original data set, and actually some of these are not, are not natural images at all. They're actually synthetically generated. So what we've done in order to achieve that is, you know, we've taken the original data set and using a technique which I'll just explain, we have increased the number of samples, particularly in categories that are having fewer samples, so that our risk or the probability of error comes down, so that my prediction gets better. How do we do that? So we'll come to that. The other part is, you can see on the left side, you have X-ray images taken at all kinds of angles. And on the right side, we used another, technique called spatial transformers to really make sure that all these images get normalized. So you will see that the size of the images on the right and sorry, the orientation as well of the images on the right is, like more more uniform. So there's less variability in the images on the right than the images on the left. And if I'm trying to do implant recognition, this gives us a real boost in the accuracy, because now the variability in these original images, which was causing some confusion, has really gone away. So what do these spatial transformers do? They're trying to do what a radiologist would do. If the X-ray is tilted, he'll try and turn the X-ray image so that he can see it from either a vertical or horizontal kind of orientation. And that's exactly what this transformer network is doing. It's figuring out what is the kind of tilt here, what's the kind of distortion here, and it's correcting for that. Let's look at this equation again. So as I mentioned, if the number of samples is small, then what do you want to do? Well, you increase the number of samples. And why do you want to do that? Because that's one way of reducing this second term. If you have more samples, then this risk will come down. And at the same time, remember, since you're doing well on more samples, it even logically it would imply the chances of doing badly on test images is going to reduce. But this is really why it reduces. It reduces because the risk comes down, right? So here is the technique that we had, we developed, and it's not a neural network based technique. So given a small input data set, it's a very simple idea and it works really well. What we do is we project it onto the first few principal components and we cluster the data in that space. What does it mean? Project onto the first, let's say 3 dimensions or 4 or 10, depending on the kind of images you have or the kind of data you have. It doesn't necessarily have to be an image kind of data set. Form the clusters there. So here is a set of clusters in, let's say, a 2-dimensional space. The x-axis is eigenvector 1, y-axis is eigenvector 2. Each sample is an input sample projected onto the first 2 eigenvectors. Here is the center of this cluster. And what we are doing is first find these clusters, find the centroid of this cluster. So that's here. And now we join the centroid to each of these samples. Once you join this line, remember, points on this line lie inside this cluster. And so if I take a point, let's say midway on this line, it's well within this cluster. It's between the center and, let's say, one of these samples. And that point is very close to the original distribution. I mean, you can prove some things with it, but we'll not get into that. But let's imagine we get this sample. It's just the midpoint of this line. Now, I can, of course, I can't really use this sample here because it's in 2 dimensions. I want it back in the input data set. And what I do now is really, I project it back to the original input space. And there's a small trick to do that, requires solving an optimization problem. And that gives you an additional set of samples. So let's look at what we get by doing this. So here is a set of samples in the original data set. These are digits, these are images of digit 0 from the MNIST data set. And here is a set of samples, new set of samples that were generated. Notice that, they don't really look like the original samples you gave. They look quite different, but yet they seem to have similarities with samples of digit 0. I mean, you would also identify them as images of the digit 0. And that's because, the midpoint of the line joining the cluster with a sample is going to look like some of the samples around, but it's not going to be exactly the same. It's going to be quite different. So the advantage is we can do this very fast. And of course, we also, there are some nice ways by which you can reduce noise in these images and so on and so forth, right? So let's go back to this equation again. What's the second way in which you can reduce the second term, which is the structural risk? What do you do about that? And second term is reduce the VC dimension. So this requires a long, discussion, which of course we don't plan to do today. And that's reducing the VC dimension. What's the difficulty with doing that? Well, if you were to plot the VC dimension against the space of machine parameters, the weights of a neural network or so on, you can't actually draw this curve. This curve just, and the reason is the VC dimension is more of a concept, in abstract terms. It's not directly connected with the space of machine parameters. So how do you go about minimizing the VC dimension when you can't connect it with machine parameters? Well, what you can do is you can find bounds on this curve. You can say there is a line that bounds it from above and another function that bounds it from below. And if you can find such a bound, then, and that has a connection with machine parameters, you can then say, well, instead of minimizing VC dimension, let me minimize some function g, which is a bound on this curve with respect to machine parameters. So there's some work that we did a little while back, but since then there have been about a dozen papers on how to extend this to all kinds of situations. There's a lot of work further to this, but here is a summary of what it can get you. So here is this method was called the minimal complexity machine, and here is a measure of how small the model is if you use a method which minimizes the VC dimension as against a current, let's say a standard state-of-the-art method like support vector machines. So a model that uses 84 coefficients could be replaced with a model that just uses 3. A model that uses say 124 coefficients would be replaced with one using 10. So roughly the ratio is between 3 and 10 most of the time. But sometimes you can be really effective. Model that takes 400 coefficients could be as good as a model that just uses 3. This, of course, has implication in the case of applications you want to put on a smartphone or an IoT device and so on. Okay, if you take it to a neural network, you get a similar reduction. Something that uses a lot of weights, a neural network, you could do the same task with a network using very few. Right. And well, I'm skipping this, but basically, you can also learn better features if you do this, right? Okay. So let's come back to this problem. What was the other difficulty with this problem? The problem was the classes were all unbalanced in size. They were of very different sizes. Some of the categories had many samples, some had very few. What do you do about that? Class imbalance is a serious problem, right? It's everywhere. And one of the commonest places where we encounter it is when we solve multi-class problems by solving them using a one versus rest coding. What is a one versus rest or one hot encoding in a neural network? So what we'll say is, let's consider a problem with 10 classes, 100 samples per class. What we'll do is we'll construct 10 binary classifiers, one for each class. And each of these binary classifiers will have 100 samples from the class of interest. For example, if you're recognizing handwritten digits 0 to 9, there are 10 classifiers. The digit 0 classifier will say, given an image, whether it's digit 0 or one of the rest. That means 0 or not 0. And not 0 means it could be anything from 1 to 9, but I don't care. Similarly, for 1 and 2 and 3. So you have 10 classifiers. Each of these classifiers is going to have 100 samples in one class and 900 in the remaining. So it's very unbalanced. And therefore, in multi-class problems, class imbalance, is almost a given. What happens in this case? So let's look at a binary classification problem with just two classes, the yellow and the white. And I want to separate the yellow from the white. And if you try it, with any of the methods you have, try coding it, running it with whatever you have at hand, very often or almost always, you will get a classifier something like this. And what this does is it separates the yellow very cleanly, but it makes errors on the white. And why does it do that? Because, well, you're really trying to tell the classifier, minimize errors on the complete data set. And therefore, the errors on the 900 are going to outweigh errors on the 100. And that's why multi-class classification is very tricky. There are many ways of trying to handle it. And one of the effective ways is one that our group had developed. And what that method does is it says, instead of finding one classifier, let's find two. Let's find a yellow line that passes through the yellow samples and is far away from the white. Let's find a white line that passes through the white samples and is far away from the yellow. Now, when the yellow classifier is being built, it only cares about being far away from the white, because the distance from the yellow samples is all essentially 0. So the result is that this classifier doesn't really get disturbed by the ratio of white to yellow samples, because it only cares about the white. And similarly, the white classifier really only cares about distance from the yellow. So this is what we do in twin kind of classifiers. And what we had done in the twin support vector machine is exactly that. We essentially find two non-parallel hyperplane classifiers that are proximal or close to the individual classes and far away from the other class. This is widely used for medical data sets. There's a fair number of citations, mainly because imbalance is very common in medical or biomedical data sets. The original twin SVM required some matrix computations, and also it was not very scalable. But of course, there's a book on it. But I am not going through the maths of this. More recently, we had something called the twin neural network, which does something similar in the neural network domain. Again, tries to find classifiers, a one-hot encoding at the output, but the nature of the classification is very different. And this has some other advantages. It also has the advantage that you don't have to tune hyperparameters as much. So anyways, we have already done this. So a twin neural network has lots of advantages. Here is a graph of, for example, the AUC or ROC versus number of samples. And you can see that as you increase the number of samples, you eventually, all the other methods tend to do better with more samples. But with the twin neural network, you're already at the, let's say, the asymptote, or you're already better off even if the number of samples is small. There are other measures that one can use, for example, the F measure and so on. And once again, you find that the twin neural network is better off even when the number of samples is not large, right? And training time, you are also much faster. So the twin neural network is as fast as a standard regularized neural network. And of course, here there's really no difference with a standard neural network, but it's faster than, of course, kernel methods. So finally, I'm not going to discuss this in detail, otherwise we'll run out of time, probably at the end of the allotted time anyway. So here is a question about, so here, we all have heard about finding a needle in a haystack. And the question is, what's harder than finding the needle? So you're given this haystack and you're told there's a needle, you have to find the needle in the haystack. And if you think about it, the answer isn't, immediately obvious in the way I've asked the question. But really the question is, if I just gave you this image, you would want to find what's there other than hay in the haystack, right? And if I asked you this question and I didn't tell you that there was a needle, this is a much tougher question, because here in this case, I'm looking for the needle. I know what I'm looking for. But if I asked you what else other than hay is in this haystack, it's much tougher than finding even the needle in the haystack. How do we go about doing this? So the simplest way is, well, let's take windows in this entire image. Let's compare them with each other. And anything that looks different from everything else, from all other windows, is obviously something that contains other than hay. If you do this, you can see the complexity of doing this. If you had n windows, is the square of the number of windows, because you have to compare every window with every other. So that's n squared. And if n is large, this will take you a huge amount of time. What's the problem we want to solve with this, right? And there's another slide that does ask you the same question. It's really saying find the odd tile in this entire image. If you look carefully, you will find the first one very quickly. You will find the second one after a little time. It might take you more time to find any other. But this gets tougher if the number of tiles grows. You would find it very hard to find the answer to this. And you would want to compare every tile with every other. That's going to take you forever. What's the context of this question? So the context is today, we have genome data or gene sequencing data. We can sequence about 1 million cells a day, even more than that. And what does that mean? We take a sample, let's say a sample of blood. Each cell is broken down, and it's the gene sequence or the expressions of the genes are determined, and you get a vector of about let's say several thousand genes per cell. And what we want to find out is there any cell inside this group that looks very different from all the others? Why do we want to do that? Okay, the reason we want to do that is let's come back to this image. The reason I want to do that is, if I take a drop of blood, we know that tumor cells or tumors actually shed cells into the bloodstream. So if I take a drop of blood, there are very small number of, let's say 5 or less, or maybe 5 to 10 tumor cells amongst a group of 100,000. The tumor cells don't look like other cells. They're very different, and they're all in some sense unique in terms of even the patient and the kind of tumor. So you're really not asking for a pattern. You're saying what's different from everything else. Now, finding those 5 in 100,000, and where the number of genes is again of the order of several thousand, is a really, really tough problem. And if you have 100,000 cells, then doing n squared comparisons is just impossible. So the last bit is this work that which Dr. Bhatnagar mentioned, which came up in Nature Communications. This was work done with Professor Devarkar Sengupta and 2 of the PhD students at IIT Delhi, Ashi and Prashant. And the method that we invented is called FIRE. And basically the F1 score of FIRE is way better than other state-of-the-art methods which were there at the time of the paper. Today there are newer methods, but FIRE is still amongst the state-of-the-art. It's really, really fast. It's also very discriminating. You can figure out these the rare cell groups in a very, very small, very, very small group. So you can see it identifies this. It doesn't get confused by many other groups. So you can see that the rare gets marked, elsewhere as well, right? Here is the time taken by FIRE. So FIRE runs in almost linear time, and it uses hashing methods to essentially achieve the speed up. But the other methods you can see seem to be growing faster than linear. I mean, typically they would be actually growing exponentially. So I'm not going to get into all this in detail, but let me stop here. Thank you for your attention, and if there are any questions, please let me know. You can look at that. Yeah, thanks, Dr. Bhatnagar. If there are any questions, I can take them at this point.
Thank you, Professor Jairaj. It was really very, and I'm sure our participants have some questions. So probably we could have a couple of questions with Sir. Yeah. The session is open for discussions for another 5 minutes. Students can post your questions in the chat box.
Sir, if I may ask a question with you,
Yeah, please.
I hope I'm audible.
Yeah, you're audible. Can you hear me?
Okay. So, when you are dealing with imaging data, how important it is, like, to for the classification of the samples, and how do I work on if there are some samples which have not been classified properly, and there are biased that happens with the data points being very dissimilar. So if you could just help me with this point, that how do we deal with such kind of problems when we are dealing with medical imaging data?
Can you elaborate on your question, maybe with an example or something? Yeah, can you elaborate using some example? I didn't exactly understand your question. If you can.
Okay, so if I have like 100 images, and first the data points are quite less to make some kind of a prediction. That's one of the things that I am facing. Like, when I work on some data, like let's say I work on like reproductive medicine. So the endometrium data, the sample data size is so less. So then the model that I build on is always having not the real world accuracy, of course. So it is very less. So how can I deal with such situations in real time? Any suggestions you could help us with?
So really, when you have small amounts of data, there are two things that we come immediately to mind. Of course, each problem has some other unique aspects. So eventually, one has to look at it. Let's say almost in an individual or customized sense. So first is like I mentioned, reducing the dimensionality of the data is a common thing we do when right we try to do if the input dimension is high, and with image data that's always the case, right? Very often, so in the case of deep learning methods, we have some advantage in terms of using transfer learning. So the networks trained with variety of other images are able to learn features that help or that could help in the classification of very different kinds of images. But that should be taken with a pinch of salt. It needs more careful analysis. But what are we really doing there? We are using, in some sense, some other kinds of images to increase the data set that we are able to work with. So the simpler way would be, can we increase the size of the data set itself? I didn't talk about it today. We have a newer method that's not published at the moment. This is why I didn't mention it. But today we can take a data set with, say, just about 60 samples and turn it into a data set with about, let's say about 1 million or so. With some bound on how close these newer samples are to the original data set, right? But again, like I said, how effective this is would depend on the data set. This method, we've tried it on about 100 data sets. On some data sets, we get improvements of the order of about 15%. So compared to training on the original data set, which is very small, you could improve the classification accuracy by almost 10 to 15%. But but that's not a claim. The reason is that it would depend on the nature of the data set, and we still, I would say, don't understand our method completely, right? So that's one. The other part with small number of samples is definitely you need to have some way of controlling model complexity. And if you can control model complexity, then you tend to do much better. And the improvement is clearly more visible when you have, let's say, a small number of samples. When you have a large number of samples, the improvement, by using model complexity control doesn't amount to very much. You don't see noticeable differences.
Right.
But with small data sets, you do. The other, the other kind of pointer there is that, so maybe, the rest should be reserved for an offline discussion. It's right. It's a
Sure,
bit of
sir. Sure. sometime soon. Thank you, sir. Thank you so much.
You're welcome.
Thank you so much, Professor Jairaj. Thank you so much for your time and your wonderful talk. I'm glad to invite Dr. Sarat Janga, Professor Bioinformatics, Data Science, Indiana University. Dr. Janga has a very enriched academic profile and holds an integrated BTech, MTech in biochemical engineering and biotechnology. He was awarded a PhD in molecular and systems biology, University of Cambridge, followed by a postdoctoral research at the Institute for Genomic Biology, University of Illinois at Urbana-Champaign. I would like to invite you, sir, to share a few words.
Thank you, Dr. Ankur. Thanks for having
Also,
me
I would
here
like to
today.
just add, before he starts, he is the convener from our partner university. May you please, sir?
Yeah, thank you. Sure. Can you see my screen?
Your screen is visible, sir.
Thank you. All right. So, okay, let's get started. Yeah, this is about 7 o'clock for me in the morning. So I'll try to be brief, and we are a bit late for the session. So, and I'm also talking tomorrow along with my postdoc and PhD student running a tutorial. So what I'll do today is I'll try to be brief, give a very quick overview, and then maybe we can elaborate more tomorrow when we have the workshop. So this is me, Sarat Janga. I'm an associate professor of bioinformatics and data science in the Department of Biohealth Informatics. We have pretty long school names. We used to be called School of Informatics, and then School of Informatics and Computing. And then we got funding from LUDI. So it becomes LUDI School of Informatics, Computing and Engineering. And that's some history for those of you who are interested in knowing about the IUPUI campus, which is also long, which is going to be shortened next year, and it will become Indiana University in Indianapolis. So that's some more history, a lot of changes on our campus. I happen to be also in the School of Medicine in the Medical and Molecular Genetics and Center for Computational Biology as adjuncts. My lab historically has been working on genomics and computational biology, but in the recent years, we have been also delving into imaging and other kind of modalities and the integration thereof. I'll try to give a glimpse of those prior efforts as well as what we are trying to do as of now. So the research in the lab broadly is funded by both government agencies like National Institutes of Health, as well as industry partners. We're also fortunate to get some funding support from Indo-US virtual networks, from IUSSTF, and and more recently, we have been fortunate to get funding for training students from National Library of Medicine on biomedical data science. So that's some history and the kind of funding that the lab is supported by. So as I said, historically, we are an omics and RNA omics and genomics and computational biology lab. The kind of projects that we've been heavily focused on are developing experimental and computational methods. Yeah, you heard that right. We also have a small experimental component, although we are predominantly computational, where our goal is to understand how RNA and proteins interact in the cell, how RNA is formed, how RNA interacts with protein, how RNAs are structured. So anything related to RNA is of interest, and we have been doing both experimental and computational work. And if you have heard about CRISPR-Cas9 or CRISPR-Cas13, we have also have done some CRISPR-Cas13 where we perturb RNA and to see the impact on the local RNA or local protein concentration levels. When I say local, I'm talking about cis, the immediate gene of interest. So we have done some CRISPR studies in the past. And in the last 4 or 5 years, or a bit longer, we've been also excited in nanopore sequencing. This is where my bioengineering or biochemical engineering background comes into picture. We have used these benchtop sequencing devices to sequence SARS-CoV-2 and other kinds of viral or even human RNAs, not just DNA, but actually our sequencing of the RNA itself, because this platform allows directly sequencing the RNA without the need for conversion into a cDNA molecule. And these kind of new data sets pose new data challenges, because here the raw data is actually current, electric current, and the process data is actually nucleotide bases. But how do you go from this current to the basis is an important data mining or bioinformatics or computer science challenge. And we have been developing algorithms for conversion of these electric currents into bases. And if I have time tomorrow, I will delve a bit more into these efforts. So the work from the lab has resulted in a number of different databases and software tools. For instance, in the left here, you see our efforts to integrate multi-omics data from different sources to generate large-scale RNA protein interaction networks, and how these networks change in different conditions, healthy and disease states, or sometimes we are interested in looking at the evolutionary changes in these interactions across species. On the bottom, you see an animation for nanopore sequencing. This is an example of a single nanopore pushing a double-stranded DNA into the pore. And on the inset, again in the animation, you see the current generated. The idea here is to use this current to figure out what are the nucleotide bases. And if you're thinking the current is going to give you 1:1 kind of a relationship, it's not so. It's much more complex. At any given point, there are 5 nucleotides in the pore, and the current that is generated is a moving average, and hence the problem becomes more challenging than simple conversion of current to the nucleotide basis. Again, in the middle, you see some work from us on doing synthetic biology. We do generate synthetic RNA molecules and then sequence through nanopore to get reference standards, which will enable us to develop machine learning algorithms. Again, I'm trying to be very brief, but hopefully this gives you a gist of the range of problems from a simple biochemistry all the way to bioengineering and computational analysis that we end up doing in these engineering problems. On the right, you see a series of tools. Databases such as ReadDB are very widely used for studying RNA binding protein dynamics. These are the proteins which interact with the RNA. We are heavily vested in RNA biology, as I said. It so happens that thanks to COVID, RNA has become more fancy, but we've been involved in RNA biology for quite some time. We have developed databases specifically for diseases of eye. For instance, Express is a database for gene expression in developmental stages of the eye. Or iSplicer is a tool for understanding which RNA isoforms are spliced out. Lantern is a database for long non-coding RNAs. Satan is a tool that we have developed for how proteins interact with RNA, and so on and so forth. So in all these, I'm not talking too much about the architectures of the databases or the models that are developed, but they should give you a flavor for the work we do in the genomics and the RNA biology space. And when we work with a wide range of models, we are not limited to SVMs or the SVMs or CNN. It depends on the problem. So with that brief overview, let me get into the problem at hand today. So a few years ago, we have been approached by one of the clinical ophthalmologists on our campus to see if we can actually develop models for diabetic retinopathy detection. And the problem goes as follows. Well, let's start with diabetes. Diabetes, everybody probably should know at some point that families are affected with diabetes as the world population gets more obese. It's a chronic disease in which individuals produce little or no insulin, and insulin's levels dictate the blood sugar, and thereby this stimulates the blood glucose uptake. Now, when people suffer from diabetes, at some point, there is onset of diabetic retinopathy. This is defined as a progressive disorder characterized by damage to the blood vessels that is supplied to the retina. And retina is made of rod and cone cells, which enable this vision. And when the blood vessels which are supplying, which supply to the blood to the retina are affected because of diabetes, there is significant impact on the visibility for these individuals. And it could start with simple vision impairments to blindness if it is not checked in a proper time. So what are the different stages of diabetic retinopathy? And before I get into this descriptions of these diabetic retinopathy stages, let me mention a couple of things about the images that you see. These are called fundus images. And fundus images basically describe the retinal layout of an individual. And when you say these images are taken, we were talking about two samples for individual, because you can take a left and right eye, and that increases simply the count of the samples that you can access. Sometimes it also helps in validating the reproducibility of the model when you train on one and and test on the other eye and so on. So these images here shown on the leftmost indicate, for instance, no disease visible. And as the disease progresses, the diabetic retinopathy, the first class is called NPDR, which is mild non-proliferative diabetic retinopathy. And this is often referred to, okay, and I'm talking, most of it is from textbook knowledge, and a lot of things change when you start talking to clinicians. That's where the life of an informatician gets harder. So the NPDR is defined as localized swelling of small blood vessels in the retina. And scientifically, these are defined as microaneurysms, okay? Now, a moderate NPDR, for instance, is described as everything that is found in the mild plus small bleeds, okay? There are small bleeds that are seen on this in moderate NPDR. And this could also include some leaks, or there are some small blood vessels which have closure. These are called as cotton wool spots. We'll talk more about these features tomorrow. Today, my goal is to give you a very high-level view of the problem that we are trying to work. The next stage is severe NPDR, where we are looking at anything associated with moderate NPDR plus further damage to the blood vessels. And then when we move on to the PDR, everything that is found in a severe NPDR, plus there could be new vessel formations because of disruptions in blood flow. There could be new vessels that could be formed, and that could start resulting in further leakages and further damage to the retina. And there could be detachments as a natural process of this progression of this disease. Now, if you look at these images, you may say, yeah, I think I see difference. And there may be a class or two that I could probably predict. But when you start talking to clinicians, the way these gradings of these diseases happen, it's much more complex, because there's not one or two factors. And a lot of these descriptions I mentioned are textual. But how do you convert these into models which can actually bring about accuracy from this classification? And this is where classification of these disease standards come into picture, and how do you deploy these into the models. So this is where I bring up the problem. So this classification of these retinal images has been of interest to us in collaboration with the clinical ophthalmologists and data annotators and data miners in my lab. So we have been initially focusing on transfer learning models, which have been very powerful at transferring on features from images. And we have had some good success. I would say 80–90% kind of success. But there are still challenges when you're starting to work on transfer learning, because transfer learning models do not necessarily capture the domain knowledge that you are actually looking at. In this particular case, fundus images, ophthalmology images may not be in enough number when you're using these publicly available transfer learning models. So although, as I said, we have some success, we have also had challenges. And I'm going to be talking in tomorrow's workshop more about what are the different efforts that we have been putting in using this transfer learning, as well as the more feature-based. But let me quickly go over one other image, and we'll stop the show today. So you recall I was mentioning about the different Lessian features. One approach could be, can magically a model learn any and everything in these images if you tell that this is class 1, class 2, class 3, based on using some transfer learning approach, right? The other approach is more feature based, as if a human is doing this. If you talk to a clinical ophthalmologist, how would they do it? And this is how we started trying to do it using the machines. And what I mean by that is, if a typical ophthalmologist looks at it, they would start looking at what are the microaneurysms, and they would learn from textbook, and then somebody is getting trained on what are these are leakages from small blood vessels. Let me start marking these on these images, okay? And let me quantify that. And what are these exudates? Let's say these are fatty deposits caused by breakdown of blood retinal barrier. They're comprised of leaked serum proteins. And somebody would tell you, right, this is a knowledge. And we want to capture each of these elements, whether it is hemorrhages, whether it's cotton wool spots, neovascularization, vitreous hemorrhage, or fibrous proliferation. We want to start annotating each of these features and then develop models which can specifically extract these individual elements from these images. That's a painstaking job, but it's going to pay off, as you will see in my results from tomorrow. We started extracting, developing models for each of these. And fortunately, thanks to great architectures like UNIT and others, we can extract these with a very high accuracy, 99.9 sometimes, these individual features compared to human annotators. Now, once you start extracting these features and you start scaling up your images, again, we had this discussion on sample numbers. You can do augmentation. You can try to do different kinds of augmentation. You can try to use public and all kinds of sources of data that you have at hand, normalize the data, and that can increase the quantity of data for these annotation. And you now can also do crowd annotation, right? You can ask support from groups of ophthalmologists to increase the number of samples. And we have done any and all these efforts to increase our sample size. We've used UK Biobank, that's another repository which houses a large number of fundus images, and that has increased our classification of these diabetic retinopathy stages to 95% accuracy, independently validated from clinicians. So I think that should give you a glimpse of the kind of efforts that we're putting in the diabetic retinopathy field. We will not be talking, but I just want to briefly mention that we have had interest in dental informatics. We look at X-rays from dental images. Our goal is to identify a lot of different features, such as missing and broken teeth, root canals, and bridges, and all kinds of interesting things that dentists routinely do on these images. And for this, we are working again with our dental school here. Fortunately, we have good collaboration with the dental informaticians who provide those images for us. So that part I'll keep it very brief because it's a significant work in progress. Another brief aspect, you remember I was mentioning about using unit models for extracting different features. For instance, you can extract hemorrhages, exudates, and all kinds of these elements can be extracted. They can be quantified. Individual elements can be quantified, and then they can be used into classification models. The beauty and the power of these approaches is, if you read like a clinician, you can extract as if a human is extracting these features. You can put these human interpretable AI models, which can be more appreciated by clinicians, as opposed to black box models that routinely appear in if you're just using transfer learning. And that's my 2 cents understanding of the years of work that we have been doing in these classification models. I think I have one more slide, and then I'll stop for today. This slide basically shows you the kind of accuracies that you can get for extracting various elements using, for instance, training on each of these features. by human annotators. When humans annotate and you build models using unit architecture, for instance, you can get for most of these pretty high accuracies for extracting these features. And if these features can be extracted with a very high accuracy, it naturally becomes a simplified problem to start building human interpretable models for ophthalmology diseases, not just one eye disease, but you can use these models for a wide range of eye diseases. So I'm a strong believer of interpretable AI, because non-interpretable AI cannot help you to improve model performance, because you're just going in circles and you don't know what aspect of the model can be improved. I think I'll stop there and I'll skip all these slides. This is the work of a lot of people. Doa Salam, she's a postdoc computational scientist in the lab who has done most of the work. But innovative stuff comes from a talented grad student, Hunter Gill. Both of them will be joining you folks tomorrow to give a workshop on how do you do segmentation of images, how do you annotate images, how do you extract one or two specific features. There are other people on this who have contributed to the other aspects such as nanopore sequencing, and which is again itself a whole world of work in itself. So I think I'll stop here, but we'll continue tomorrow.
Thank you, Professor Janga. It was really an informative and a very wonderful talk, and I'm sure students are going to really enjoy your session tomorrow. Looking forward to seeing you tomorrow again, sir. So now, as we come to the end of our session, may I please request Dr. Priyanka Narad, Assistant Professor, Center for Computational Biology and Bioinformatics, Amity Institute of Biotechnology, to please deliver the vote of thanks. Over to you, ma'am.
Thank you, Dr. Devlina. I hope I'm audible. I, Dr. Priyanka Narad, on behalf of Amity Institute of Biotechnology, Amity University, Uttar Pradesh, would like to express my gratitude to our respected founder president, Dr. Ashok K. Chauhan sir, our dynamic chancellor, Dr. Atul Chauhan sir, for being our guiding source of inspiration. I would like to express my gratitude to our motivating Honorable Vice Chancellor, Professor Dr. Balvinder Shukla ma'am, for being the catalyst that stimulated us to do our best and standing as our pillar of strength. I would like to take this opportunity to put all my appreciation in the form of words towards our esteemed speakers, Dr. Jayadeva and Dr. Sarat Janga, for their excellent lecture and research insights. I would also like to express my sincere thanks to Dr. Pooja Vijay Raghavan, officiating head AIB, for her guidance and support at every step of the preparation. I would also like to place on record my deep appreciation to Dr. Seema Bhatnagar, Assistant Director AIB and convener of this symposium, for helping and planning all the tiniest of details for the symposium. I would like to thank all the respected heads of institutions, center heads, faculty members, and office support who have blessed us with their presence for encouraging us throughout the session. I would also like to appreciate the whole team of the symposium, student volunteers, IT support, and admin for all the necessary arrangements. Last but not the least, I thank everyone for their attention. Thank you everyone for joining. I hope you have a great symposium ahead.